Okay, this section is on the binomial distribution. A couple of things to know about the binomial distribution is it is a discrete distribution, meaning it's based on a discrete random variable, not on a continuous random variable. That means the possible values that can be used on this are values, let's say, like 0, 1, 2, 3, etc. So it's based on a discrete random variable. Now these values for the discrete random variable, RV stands for random variable, can take on values, like I said, 0, 1, 2, 3, 4, 5, etc. Now sometimes it might not start till 7, 8, 9, 10, but the whole point is it takes on integer values. It's also based on a binomial experiment. Now like the prefix BI says, there's two different outcomes. Like bicycle has two wheels, there's two different possible outcomes for a binomial experiment. So these are the things that we want to keep in mind. Now there's a list of certain characteristics for a binomial experiment. So let's go ahead and look at a binomial experiment. There's 4 things that we need to kind of keep track of here. Now when we're talking about a binomial experiment, the first thing that we're looking at is we know when we run this experiment that there's a fixed number of n trials. So n is the number of trials here. So before we start the experiment, we know that we're going to do the experiment, flip a coin, roll a die, etc. 20 times or 25 times before we start. And this value has to be known in advance. I can't change the rules as we go. I can't say, well, I'm going to do this 20 times and see what happens and then decide, well, maybe I'll do it 22 times or something like that. It has to be fixed and it has to be known in advance. The next criteria is each trial, each flip of the coin or roll of the dice, has to have 2 possible outcomes. Exactly 2 possible outcomes. Now these 2 possible outcomes can be either classified as a success or a failure. Now just because we have the word success and failure, the successful outcome doesn't always have a positive connotation and the negative outcome doesn't always have the failure connotation. We kind of try and write these to match the situation that we need. Now, when I was talking about rolling a dice, you might say, well, wait a minute, there's 6 possible outcomes there. But we could be looking for something like the probability of rolling an even versus the probability of rolling an odd, and then that would be where we'd have 2 possible outcomes. So it depends on the outcomes that we're looking for. The third criteria, the trials must be independent and identically performed. So the trials must be independent and identically performed. That means when I run one trial, it's not going to affect the outcome of the other one. Okay, the fourth criteria, the probability of a success has to be the same for every trial. So the probability of a success, probability, has to be the same. So we say is constant from trial to trial. Now, when we start talking about these and we know we have a binomial experiment, we can start writing down some notation. If I have a binomial experiment, you usually have a random variable x that you're talking about. And x is usually counted as the number of successes. Again, we can define success however we want. The number of successes out of the n trials. Remember, the number of trials we know in advance. Well, if this is a situation and all 4 of these criteria are met, then we say x is distributed as binomial. This little tilde sign means distributed as binomial n p, where of course n equals the number of trials known in advance, and p equals the probability of a success. And then the probability of success we know is constant from trial to trial. Now, a couple of other things that come up here then. I know how to find this probability. Let's say the probability that x equals some value, and this x is a lowercase x is a realization of the random variable. This is equal to the number of combinations of n choose x, the probability of a success to the x, times 1 minus the probability of a success to the n minus x. Now this 1 minus p right here is actually equal to q. that's 1 minus p, that's the probability of a failure. So a lot of times you'll see this written as a cube. Now this is a really nice little distribution. It's easy to find these values, and we'll look at some examples where we can find these by hand, but we'll also look at how we can use your calculator as a shortcut. Now given this distribution, the mean of this distribution is n times p. The variance of this distribution is n times p times q. So the standard deviation of this distribution is the square root of the variance, or the square root of n times p times q. Now remember, q is 1 minus the probability of success, or the probability of a failure. So these are some important things to know, and we'll look at some shortcuts that we can use on our calculators here in a moment. For our first example, let's go ahead and suppose, and again this is an S with a P hanging from it, so it means suppose. So suppose you are going to eat out. At 10 different restaurants on a vacation. And as you are doing some reading about this, eating out at these restaurants on your vacation, you read that 3 out of 7 restaurants have some sort of a health code violation where you're traveling to. Now we don't know what type of health code violation, we just know there's been a violation. And we don't know which restaurants have this, we just know that on average about 3 out of 7 restaurants have a health code violation. So the first thing that we're going to wonder about is this a binomial experiment? Now if it is a binomial experiment, then I can start applying some of those probabilities that I have up top. Now remember, if it's a binomial experiment, it will meet 4 criteria. 1, I have a fixed number of n trials. And in this case, n is 10, because I'm going to eat out at 10 different restaurants. And I know in advance that there's going to be 10 restaurants. 2, each trial has 2 possible outcomes. So each restaurant I go to visit, that's a trial. Now with these 2 possible outcomes, there will be deemed as a success or a failure. And so this is when we have to start defining what success and failure mean. Now for this example, a success would be pass inspection. And so the opposite of passing would of course would be failing inspection. Okay, third criteria. What happens here is they are independent and identically perform trials. So that means I go to the restaurants, I do the same thing, I eat there, I see if they passed inspection or not. So the fact that my first restaurant fails doesn't mean my second one will fail, or there's no influence between the restaurants. They're all independent, passing or failing. The fourth, the probability of success is constant. So in this case, the probability of success is constant. And I know that it is constant. If we look up here, we see that 3 out of the 7 restaurants have a health code violation. So the probability of failing is 3 out of 7. So that would mean the probability of success then, the probability of passing, would be 4 out of 7. And that's constant from trial to trial. So yes, it is a binomial experiment because it's met all 4 of the criteria. So what we do now is we try and figure out some probability statements that I could write, and I define my random variable. So to summarize here, yes, this is a binomial experiment. Now when we talk that it's a binomial experiment, then I can define the random variable x. X is equal to the number of restaurants out of 10 that pass inspection. Okay, Now, because I know my random variable x is based on a binomial experiment, I said x is distributed as binomial n. N is the number of trials. P is the probability of success, 4/7. So again, this is n and this is p. So to get started, I could do all sorts of different things. I could find the average, the expected value. So if I wanted to do that, the mean number of restaurants that pass inspection, the formula here is NP from up above. I would take the number of trials times the probability of a success, and I'd get 10 times 4, which would be 40 here, and then divide that by 7. And it looks like to me, if I rounded this, let's say, to the nearest tenth, I would get 5.7 restaurants would pass. Because remember, this is based on successes. So 5.7 on average restaurants would pass inspection out of 10 that you visit. Okay, so remember, x is the number of successes or passes. Okay, now next we can look at the variance, and we're actually not all that interested in the variance. We just find the variance to get to the standard deviation. So it would be 10, 4/7 times 3/7. It would be 40 times 3, it would be 120 over 49. And this would be restaurants squared. But we don't like to deal with things like restaurants squared. We like things to be in the same number of units. So what we do then is we take the square root of the 120 over 49, and let's go ahead and round that to the nearest tenth as well. So 120 divided by 49, and I'd get here 2.4 is the standard deviation. 2.4 restaurants pass inspection. That's my standard deviation. Okay, and I can do all sorts of different things from here. I could look at what is the usual amount. So remember, what usual meant was my mean plus or minus 2 standard deviations. So for this case, it would be 5.7 plus or minus 2 sigma. Sigma was 2.4. So that would be 5.7 plus or minus 4.8. Now to find the lower end, then, I would take 5.7 minus 4.8. And then to find my upper end, I would take 5.7 plus 4.8. So for my lower end, I have that 5.7 minus 4.8. And I would have 0.9 restaurants on the lower end. And then on my upper end, and again, that 0.9 really doesn't make sense because our integer values are what we're looking at here. This would go all the way up to 10.5. So the usual range would be between, it looks like 0.9 and 10.5. This would be usual. So 0 restaurants passing inspection would be unusual because it's the only one that doesn't fall outside this range. Remember, this is how we find usual, going from 0.9 to 10.5 restaurants. And we can answer a lot of probability questions from here as well. For instance, we could say, what is the probability that exactly 1 restaurant passes inspection? Now this is 1 out of the 10 that you visit. So the probability statement here, remember x is the number of passes. This is the probability that x equals 1. Well, from our formula up above, this would be 10 choose 1. P, probability of success to the first. Q, 3/7 probability of a failure to the 10 minus 1. So this would be C, 10 choose 1, 4/7 to the first, 3/7 to the 9th. Okay, and you can plug and chug that through your calculator and see what you get for a decimal approximation. And then I'll show you a shortcut as well on your calculator because it has a binomial function. So go ahead and give that a try. Okay, I'm going to see if I can pull my calculator in here to show this calculation. Okay, so to get started with this calculation, first we need combinations. So under combinations, we'd want to start with the 10 first, and some of your calculators might work a little differently. On mine, then you go across to probability, and I go down to the combinations option, and then I put in 10 choose 1. Okay, now I want to make sure I arrow out of that subscript 1, and I want to multiply this by, and I'm putting in parentheses as well, which is probably a little bit of overkill, but I need to have parentheses to make sure I'm getting this raised to the first power. And I know that I don't have to show that it's raised to the first power because anything to the first power is just itself. But I just want to make sure I show all the steps here, and this would be 3/7 to the 9th. Okay, and so that output should give me the same value for that combination times those corresponding probabilities. Okay, so let's go ahead and see if we can compare this to what the output of the calculator would be using a different mode. Now if we were to round this, we would probably round this to something like 0.003. Now be careful when you're working in My Math Lab, because it'll be pretty specific. Sometimes it'll ask you to round to the nearest 3 decimals, sometimes to the nearest 4, so just make sure you're specific about that. Now let's go ahead and do the same problem, but in this time let's use another function in your calculator called the binomial PDF. This is located under DISTR. It's this blue menu right across or right above the vars key. So I'd go second distribution, and I'm going to either scroll up or down, it doesn't matter, until you get to binomial PDF. So here I am, binomial PDF. Now be careful, because right underneath of that we have binomial CDF, and we want to work with binomial PDF. And you go ahead and hit enter. Now the first thing it asks me for is the number of trials, which I know are 10. The probability of a success is 4 divided by 7. We'll see if it'll take a fraction. Now the x value that I'm interested in is x equal 1, because that was my probability statement. And then I see my shortcut here, binomial PDF, 10, 4/7, 1. And you can see I get the exact same value here, and it's a little bit shorter. I don't have to crunch quite so many numbers. But in order to get started, I still need to know the same information, and that same information is what are our values for n, what are our values for p, and then of course x. So you can see we get the same exact answer here either way. Let's go ahead and look at a little bit more difficult problem. It's still going to be the same distribution that we're talking about up above. What is the probability for this same type of problem? But now what I want to know is what is the probability of at least one restaurant passing? Now when we say at least one restaurant, that is really quite a bit of calculations to go through. Because the probability of at least one would be 1, probability of x equal 1, plus the probability of x equal 2, because this is at least. And this is going to go all the way up to 10. And I don't want to find all of these probabilities 1 through 10. So the easier way to think about this is the complement. The possible values are 0 through 10. So the easier way for me to think about this is 1 minus the probability that x equals 0, because it's the only value that's not accounted for. So the probability of x equals 0, that's pretty easy to work with. That would be this combination. I'd have 10 choose 0 this time, 4/7 to the 0, 3/7 to the 10 minus 0. Or you can go ahead and just use your binomial value in your calculator, and let's see how that will work. So opening up your calculator, you'd go 1 minus the binomial distribution, and that's in the blue letters, DISTR. And we'd go to the binomial PDF. It's letter A on my calculator. It might be something different on yours. Okay, there's that binomial PDF. Now remember, there's a CDF. I want to make sure I'm at the PDF. And it usually pulls the values that I use last, so this is nice. I know I have n trials. Probability of success is 4/7, but now this time my x value that I'm looking for is 0. Now if you wanted to, you could look all of these up. So here's 1 minus that binomial distribution, and I get 0.99979. So that is my answer. I'll copy that. And again, the calculator kind of gave me that shortcut to finding that value. So here, if they asked me to round to 3 places, I'd have to end up rounding this to 1. So I think I'll round this one to 4 places, and I'd have 0.9998 for the probability of at least one restaurant passing. So what is the probability of these 10 restaurants that I visit, at least one that I visit will have passed inspection? It looks like it's a very, very high probability. Now be careful when you're working again, because it will be pretty specific about how it wants you to round in my math lab. Let's go ahead and look at another example. Now in this example, we're looking at an airline that overbooks flights. And the reason the airline overbooks flights is some people don't show up for their flight, and so they'd have empty seats. And so if they overbook, there's 2 possible outcomes. They could have somebody not show up and still have enough seats, or maybe they'll have overbooked and everyone shows up, and then they're going to have to probably give away a free ticket or something for that person that they overbooked with. So as we're reading this, it says an airline has a policy of booking as many as 25 persons on an airplane that can seat only 24. Okay. Past studies have revealed that only 87% of booked passengers actually arrive for the flight. Find the probability that if the airline books 25 persons, not enough seats will be available. Okay, so first of all, is this a binomial experiment? And if you think about it, as each person either shows up or doesn't show up, there's 2 different outcomes, success or failure. So 1, do I know my fixed number of n trials? And I do. N is 25 trials known in advance. Okay, second, when we're looking at the different criteria, I have 2 possible outcomes. So my outcomes are success and failure. And so a success would be if a person comes and they show up to their flight. A failure would be a no-show. The third criteria is they're independent. And we'll have to say that they are independent for this example. I guess the only thing that I can think of was where it wouldn't be is if a whole family was traveling together, and if one missed, they all missed because they were showing up at the same time. But we'll assume independence here. And then we have the probability of a success. Now remember, success means they show up. So here, 87% of passengers actually arrive for the flight, so that's 0.87. So I should be able to define my random variable x. X is equal to the number of passengers who show up for their flight out of the 25 that are booked. Now the question here is, if we kind of run back up, the probability that not enough seats will be available. Well, the only way that not enough seats will be available is if 25 people show up. If only 24 show up, I'm good. But the problem is when 25 show up. So this is my distribution. X is distributed binomially. N is 25. P is the probability of success is 0.87. And so I can just go ahead and crunch this through. If you want to do this the longhand, you can. This would be 25 choose 25 times 0.87 to the 25th times 0.13, which is the complement of 0.87 to the 0. Okay, or we can use our calculator distribution function. So let's go ahead and try that. So this would be our binomial distribution, which is second distribution, DISTR. And you can either scroll up or down to the binomial probability. Make sure it's PDF, not CDF. Now in this case, I have 25 passengers who could show or no show. The probability of showing is 0.87, and I would like to know what's the probability that 25 people actually show up. And this is going to crunch that and tell me there's about a 3% chance that'll happen. Okay, and that's from this right here. And again, you can do these by hand and with your calculator. It's probably not a bad idea to do both. So if we were to round this to the nearest 3 places, the probability of not enough seats is pretty small in this case. So this would be the probability of 0.031 if we rounded that to the nearest thousands. So the probability that they overbook the flight is only about 3%, given the long-term distribution of how people arrive or show or not show for the airplane flights. So working with the binomial distribution is actually pretty straightforward. We already have an idea what usual and unusual mean, so we have enough information to talk quite a bit about the binomial distribution in terms of finding probability, in terms of finding the mean, and then talking about things like the usual and the unusual. If you have any questions with this section, please let me know and be happy to help you out. Good luck.